There is a 3-digit number that physicists write on scraps of paper and pin above their desks, not as a joke and not as decoration. Richard Feynman said every good theorist keeps it on the wall and worries about it. Why does a natural nuclear reactor that switched itself on in Gabon 2 billion years ago count as evidence about that number? Why have the 2 most precise atomic laboratories on Earth disagreed about its 10th decimal place for 6 straight years, with neither team able to find its own mistake? And why did one of the finest mathematicians of the 20th century stand up at 89 years old in front of an international audience and stake what was left of his reputation on explaining it? 3 months before he died? Those are not 3 stories. They are 1, and the same number sits underneath all of them. By the time you understand why nobody can account for it, the number will be the least unsettling part of this. Get comfortable, because this ends somewhere I did not expect when I started reading. Physics has never explained the value of anything, not once, in 400 years. If you want these episodes without ads, they live over on our Patreon, Meridian Labs, which this channel is part of, alongside early access and an audio-only feed for listening with the screen off. Subscribe or join if you have not. Let's start where it started. On the 15th of December, 1958, one of the most feared minds in the history of physics was dying of pancreatic cancer in a hospital in Zurich. His name was Wolfgang Pauli. He had won the Nobel Prize 13 years earlier. He was the man who had terrified Einstein, corrected Heisenberg in public, and predicted the existence of a particle so ghostly that it took 26 years to find. And for most of his adult life, he had been quietly, privately, almost embarrassingly obsessed with a single number. Not an equation, not a theory, a number. When his last assistant, a young physicist called Charles Enns, came to the Rockwood Hospital to visit him, Pauli did not ask about his own diagnosis. He did not ask about the pain. According to Enns, who wrote the account down decades later in his biography of Pauli, the dying man asked him one thing first. He asked whether Enns had noticed the number on the door. The room was 137. Now, I want to be careful here, because this story has been passed around physics departments for 60 years, and it has been polished by the retelling. Pauli did not choose that room. Nobody arranged it. A hospital administrator in Zurich assigned a bed to a dying professor and thought nothing of it. The coincidence is a coincidence, and Pauli, of all people, would have been the first to say so out loud, while privately being unable to let it go. But the reason the story survives is not the coincidence. It is what the number meant to him. Because Pauli believed and said in public, in front of the Swedish Academy, that quantum mechanics could not be considered finished until somebody explained where that number came from. He never got the explanation. Neither did anybody else. 27 years after Pauli died, Richard Feynman published a small book based on a series of lectures he gave in New Zealand and at Cornell. The book is called KED, The Strange Theory of Light and Matter, and it is probably the best popular account of quantum electrodynamics that has ever been written, largely because Feynman refused to lie to the reader anywhere in it. About 2/3 of the way through, in the middle of a discussion about how strongly an electron couples to a photon, he stops the physics dead and writes something that has been quoted so many times that the default assumption now is that it has been mangled somewhere along the way. It has not been mangled. I checked the actual text. Here is what he wrote. He describes the coupling constant, the number that determines how likely it is that an electron will emit or absorb a photon, and he gives its value as roughly 0.08542,455. Then he notes, in a parenthetical aside, that his physicist friends will not recognize that number because they prefer to remember it as the inverse of its square, which is about 137.03597. And then he says that it has been a mystery ever since it was discovered more than 50 years earlier, and that all good theoretical physicists put this number up on their wall and worry about it. That is the actual sentence. On their wall. Not a paraphrase, not an internet mutation, not a quote that grew legs. Feynman wrote it, and Princeton University Press printed it. And then he goes further, because Feynman was constitutionally incapable of stopping at the polite version. He asks whether the number is related to pi or to the base of natural logarithms, and answers his own question with the word nobody. Nobody knows. He calls it one of the greatest damn mysteries of physics. A magic number that comes to us with no understanding by man. He says you might say that the hand of God wrote that number, and that we do not know how he pushed his pencil. Then comes the line that I think is the actual confession, and it is the one that almost never gets quoted, because it is not mystical enough to survive on a poster. He says that we know what kind of dance to do experimentally to measure the number very accurately, but we do not know what kind of dance to do on the computer to make the number come out, without, and this is his phrasing, putting it in secretly. Read that again. One of the architects of the most accurate physical theory ever constructed is telling you that the theory cannot generate its own central number. You have to feed it in by hand. You measure it in a laboratory, you write it down, you type it into the equations, and then the equations give you predictions of extraordinary, almost obscene precision. Predictions that match reality to 12 decimal places. But the number itself comes from nowhere. It is not derived. It is not calculated. It is not implied by anything deeper. It is simply the value that reality happens to have, and every physicist on Earth is required to accept it the way you accept a phone number. This is the constant that Pauli died next to, and Feynman put on his wall. The fine structure constant. Alpha, roughly 1 divided by 137. And here is where I have to reopen something you probably think is settled, because almost everything popular science says about this number is either wrong or worse, is right about the wrong thing. It is not 1 over 137. I do not mean that as a technicality. I mean that the entire mystique of this number, the room number, the wall, the prime number numerology, the endless posts about how 137 is the only number the universe has ever handed us for free, is built on a value that stopped being correct around 1930. The best current figure, the one recommended by the Committee on Data of the International Science Council, published in Reviews of Modern Physics in 2025 and based on every measurement in the world through the end of 2022, is 130 7.035999,177, with an uncertainty in the last 2 digits. That trailing tail is not decoration. Eddington built a career on it and lost his reputation to it. 2 of the most precise experiments ever performed by human beings currently disagree about it, violently, and that disagreement has not been resolved as I am recording this. It is the reason the international body that curates the constants of nature had to do something in 2022 that they very much did not want to do, and which almost nobody outside of a few hundred metrologists has ever heard about. They will not tell you it is embarrassing. They published it in a table in a footnote in the driest language available to human beings. But it is embarrassing, and we will get to exactly what they did and why, because it is one of the quietest scandals in modern physics. And that is still not the part that should disturb you. Here is the part that should disturb you. The number on Feynman's wall was already out of date the moment he wrote it down, and not because the measurement improved. Because it is not a constant, I need to be extremely precise about what I mean by that, because there is an entire cottage industry of people claiming the constants of nature are secretly drifting, and most of them are wrong, and I am going to spend a long time later in this showing you exactly how and why the most famous claim of that type collapsed. That is not what I am talking about. I am talking about something far stranger, far better established, and completely uncontroversial among working physicists, which is precisely why nobody bothers to mention it to you. The strength of electromagnetism depends on how hard you look, not metaphorically. Measurably at the energies of everyday life, the energies of chemistry, of light, of the electron sitting in a hydrogen atom. The number is 137.036. Push to higher energy, smash particles together at the mass of the Z boson, about 91 billion electron volts, and the same quantity is not 137, it is roughly 129. 128.96, to be more careful about it, with an uncertainty of about 3 in the last 2 digits. So the number Feynman worshipped is a reading taken at a particular depth. Go deeper and it changes. It is not the constant of the universe, it is the constant at our altitude. Which raises the question this whole thing is built around, and which I am telling you now, at the start, will not be answered by the end. Because it has not been answered by anyone. Where does that number come from? Not what does it do. We know what it does. It sets the strength of the electromagnetic force, which means it sets the size of atoms, the energy of chemical bonds, the colour of the light coming off every star in the sky, the rate at which carbon is manufactured inside dying suns, and therefore, whether there is anything in the universe capable of asking the question in the first place. We know what it does with a precision that borders on the absurd. We do not know why it has the value it has, not vaguely, not partially, not almost. There is no theory, no framework, no equation, no model, and no serious candidate anywhere in physics that predicts that number from first principles. String theory does not. The standard model does not. Because the number is an input to the standard model, not an output. Loop quantum gravity does not. Nobody does, and over the next couple of hours I am going to walk you through every serious attempt anyone has made, and every one of them failed, and the way each one failed tells you something worse about the situation than the last one did. One man tried to derive it from pure logic and was laughed out of the profession while he was still alive. One man tried to derive it from the structure of the human unconscious, with the help of Carl Jung, and took it to his grave in room 137. One team spent decades and 10,000 Feynman diagrams building a theoretical prediction of a related quantity so precise it can detect the influence of particles that have not been discovered, and then 2 other teams measured the number with lasers and got answers that cannot both be true. And in 2018, one of the greatest mathematicians of the 20th century stood up in front of an audience in Heidelberg and announced he had solved it, and what happened to him in the 4 months that followed is genuinely difficult to talk about. They were not cranks. That is the thing I need you to understand before we start. Every single one of them was, at minimum, extremely good, and 2 of them were among the finest minds their fields have ever produced. This number does not attract fools. It destroys serious people. There is a reason for that, and it is not the reason you think. Munich, 1916. Europe is 2 years into the worst war it has ever seen, and Arnold Sommerfeld is sitting in the Institute for Theoretical Physics at the Ludwig Maximilian University trying to fix somebody else's atom. The atom belonged to Niels Bohr. 3 years earlier, in 1913, Bohr had produced the model that every schoolchild still gets shown. The one with the electron in circular orbits around a nucleus, jumping between fixed energy levels and spitting out a photon each time it falls. It was a strange, half-finished, internally inconsistent piece of work that nobody could justify from first principles, and it did something no theory had ever done before. It predicted the wavelengths of the light coming off hydrogen gas correctly, not approximately, correctly to the accuracy of the spectroscopy of the day. There was one problem, and it had been sitting in the literature since 1891, when Albert Michelson and Edward Morley, the same pair whose failure to detect the ether had already broken classical physics once, pointed their interferometer at hydrogen and found that the spectral lines were not lines. They were pairs, doublets, two lines sitting almost on top of each other, separated by a gap so small it was barely there. Michelson could resolve it, and Bohr could not explain it. The theory said one line: the universe was producing two. This is the first thing I want you to sit with, because the pattern repeats through this entire story and it never gets less strange. The fine structure constant did not enter physics as a grand principle, it entered as a discrepancy. A splitting in a spectral line so fine that it took one of the best instruments on Earth to see it at all, and so small that the ratio between the split and the line itself is about 1 part in 15,000. Sommerfeld's fix was to make the orbits elliptical and to apply special relativity to the electron running around them. If the orbit is an ellipse, the electron speeds up near the nucleus and slows down further out. If it speeds up, its relativistic mass changes. If its mass changes, its energy changes. And that means orbits that Bohr had treated as identical are not identical. And the single line becomes a pair. He published it in Annalen der Physik, in the 4th series, volume 51, under the title Zur Quantentheorie der Spektrallinien, which is about as unglamorous as titles get. On the quantum theory of spectral lines, 94 pages of it, and in the middle of that paper, a quantity appears that nobody asked for. To work out how much relativity distorts the orbit, you need to know how fast the electron is actually going. So Sommerfeld computed the speed of the electron in the innermost orbit of hydrogen and compared it to the speed of light. That ratio is what came out. The electron in the ground state of hydrogen is moving at about 1 part in 137 of light speed, roughly 2,200 kilometers per second, which is fast enough to cross the United States in under 2 seconds, and slow enough that relativity is only a small correction. That is what alpha originally was. A velocity ratio, a number that told you how relativistic the hydrogen atom is, which is to say, barely, and this is where the story develops its first real crack. Because Sommerfeld's model is wrong. Not slightly wrong, wrong at the foundations. There are no elliptical orbits. Electrons do not travel on paths. The entire picture of a little planet swinging around a nucleus was demolished within a decade by Heisenberg and Schrödinger, both of whom, and I am not exaggerating this for effect, were sitting in Sommerfeld's lecture rooms in Munich at the time. Heisenberg was his student. Pauli was his student. The men who destroyed his atom learned physics from him. But the formula survived. In 1928, Paul Dirac wrote down the correct relativistic quantum equation for the electron, an equation with spin built into its structure, an equation so deep it predicted antimatter as a side effect. He applied it to hydrogen and calculated the fine structure, and the expression he got was, to the order that mattered, identical to Sommerfeld's. Identical, same formula. From a completely different theory, built on completely different foundations, using an ingredient, electron spin, that Sommerfeld did not know existed. Physicists have a slightly uncomfortable name for this. They call it Sommerfeld's miracle, and if you go looking for the explanation, you will find that it is essentially a conspiracy of cancelling errors. Sommerfeld left out spin, which should have wrecked the answer. He also used a model of orbital angular momentum, but was wrong in a compensating way. The two mistakes, in the specific case of hydrogen, that the specific order of approximation he was working to happened to cancel each other exactly. Think about what that means for a moment. The number that half of theoretical physics has been staring at for a century first arrived in the literature through a model that was wrong, carried there by two errors that happened to annihilate. That should have been a warning. It was treated as a triumph. Sommerfeld himself never really pushed the mystical angle, and it is worth saying clearly that he did not consider the number to be handed down from anywhere. For him it was a measured ratio in a specific physical system. The elevation of alpha from spectroscopic bookkeeping to sacred object happened later, and it happened for a specific and, I think, defensible reason, which is the single most important technical point in this entire story. Alpha is dimensionless. I want to slow down here because this gets skipped constantly, and it is the difference between a genuine mystery and a category error. The speed of light is not a mystery. It is 300 million meters per second, or 186,000 miles per second, or 1 foot per nanosecond, or exactly 1, depending on what units you feel like using. Its numerical value carries no information about the universe. It carries information about the length of the meter, which was originally defined as 1/10,000,000th of the distance from the North Pole to the equator through Paris, a fact that tells you a great deal about French revolutionary politics and nothing whatsoever about physics. Since 2019, the situation is even blunter, because the meter is now defined in terms of the speed of light, which means asking why light travels at that speed is asking why we chose that ruler. Same for Planck's constant. Same for the charge on the electron. Same for the gravitational constant. Every one of them is a number about our measuring system wearing the costume of a number about nature. Alpha is different. Alpha is built out of the electron charge, Planck's constant, the speed of light, and the permittivity of the vacuum, and they are combined in exactly the proportions required for every unit to cancel. Meters cancel. Kilograms cancel. Seconds cancel. Coulombs cancel. What is left is a bare number with nothing attached to it, which means it is not about us. If there is a civilization on the other side of the galaxy with a different history, a different anatomy, a different definition of length based on the body of whatever they evolved from, measuring the strength of electromagnetism with instruments we would not recognize, they get 137.036. They have to. There is no convention available to them that changes it. It is one of a very small number of facts that any thinking thing anywhere in the universe is forced to agree with us about. That is why it stopped being a spectroscopic correction and became a theological object. Because when you strip out every human convention from physics, when you cancel every ruler and every clock and every arbitrary standard, a residue is left over. A handful of pure numbers that reality apparently just has. And this is the one that governs light and matter. Alpha is the answer to the question of how strongly a charged particle grabs a photon. Turn it up, and every atom in the universe contracts, and every chemical bond stiffens. Turn it down, and matter loosens, atoms swell, and the sun goes out. It is the volume knob on electromagnetism, and the setting reads 1/137.036, and nobody has ever found the hand that set it. Sommerfeld spent the rest of his life at the centre of European physics, without ever quite getting the recognition that his students got. He was nominated for the Nobel Prize 84 times. That is not a typo, and it is not folklore. It is in the official nomination archive maintained by the Nobel Foundation. 84 nominations, more than any other physicist in the history of the prize, spread across 34 years from 1917 to 1951. He never won. Meanwhile, his students collected them like stamps. Heisenberg, Pauli, Debier, Bethe, Pauling, Rabi, von Lau. 7 Nobel laureates came out of that institute, and the man who taught them all stood in the corridor and applauded. On the 26th of April, 1951, Sommerfeld was out walking in Munich with his grandchildren. He was 82, and he was very deaf. He stepped into the road and was struck by a truck he never heard coming. He died of his injuries. The last nomination in his file was submitted that same year. I am not telling you this because it is a sad anecdote to hang on the front of the physics. I am telling you because the man who first wrote that number down never claimed to understand it and never pretended to. And he was not punished for that restraint. He was simply overlooked. The people who came after him were less careful. They decided that a pure number with no units attached must be a message, and that a message must have a meaning, and that the meaning must be available to sufficiently clever reasoning. The first of them was the most famous scientist in Britain. and he was about to spend the last 15 years of his life being quietly destroyed by 3 digits. In 1919, Arthur Stanley Eddington took a boat to the island of Principe off the coast of West Africa, photographed a total solar eclipse through gaps in the cloud, measured the deflection of starlight passing the edge of the sun, and made Albert Einstein the most famous human being alive. It is hard to overstate what Eddington was. He was the Plumian Professor of Astronomy at Cambridge, Director of the Cambridge Observatory, President of the Royal Astronomical Society, and for a period in the 1920s, he was probably the most respected astrophysicist on the planet. He worked out how stars hold themselves up. He established that stellar interiors are radiation pressure balanced against gravity, which is the reason we understand the sun at all. When Einstein's theory was still viewed as continental strangeness by most of British science, Eddington read it, understood it, and went to the equator with a camera to check it. He was not a crank. I need that established before anything else, because what he did next is usually presented as a punchline and it deserves better than that. Starting around 1929, Eddington became convinced that the constants of nature were not measurements, they were consequences. He believed that if you were sufficiently rigorous about the logical structure of a theory that combined quantum mechanics and relativity, the numerical values would fall out of the mathematics the way the ratio of a circle's circumference to its diameter falls out of geometry. You would not need to go and measure them. You would derive them, sitting in a chair with a pencil, and he thought he had done it for alpha. The argument, and I am going to give you the actual shape of it rather than the caricature, went roughly like this. Dirac's relativistic electron theory operates on objects built from a set of matrices. If you take the algebra seriously and generalize it, you can count the independent components. Eddington counted 16. Then he counted the independent components of the antisymmetric combinations you can build from those 16, which is 16 times 15 divided by 2, which is 120. 120 plus 16 is 136. He published that. In the Proceedings of the Royal Society, he claimed the inverse of the fine structure constant was exactly 136, and that this was not a coincidence but a theorem derived from the degrees of freedom available to a relativistic quantum particle and the requirements of the exclusion principle. At the time, the measured value was around 136 point something, and the experimental uncertainty was large enough that you could squint. For a brief window, Eddington had done what Sommerfeld never dreamed of doing. He had explained the number. And then the spectroscopists got better. Through the early 1930s, the measurements tightened. The value did not settle at 136. It settled at 137 point something, and it kept refusing to move back. Now, this is the moment. This is the hinge on which a great scientific reputation turns, and I think it is the most instructive 30 seconds in the history of physics numerology, so I want to be exact about what he did. He wrote, more or less, that he could not persuade himself that the fault lay with the theory. And then he added one. He produced a supplementary argument. The exclusion principle means that 2 electrons in the same state are indistinguishable, and indistinguishability, he reasoned, removes a redundancy from the counting, which means you need an extra unit somewhere in the tally. 136 becomes 137. Same rigor, same confidence, new answer. He held to it for the rest of his life, and he never revised it again. The physics community, which had been prepared to be respectful while a great man had an eccentric hobby, stopped being respectful. Somebody, and the origin has been lost, started calling him Sir Arthur Adding 1. It stuck. It is still what he is remembered for by people who could not name a single thing he actually got right, which includes the internal structure of stars and the first experimental confirmation of general relativity. In 1931, 3 young physicists decided to make the point more forcefully. Guido Beck, Hans Bethe, and Wolfgang Rietzler submitted a short paper to Die Naturwissenschaften, one of the most respected German-language science journals, titled Remarks on the Quantum Theory of the Absolute Zero of Temperature. In it, they considered a crystal lattice made of neutrinos, counted the degrees of freedom in the approved Eddingtonian manner, and derived the value of absolute zero in degrees Celsius. Their result was -273. The joke, and it is a genuinely vicious joke, is arithmetic. 2 divided by alpha minus 1 is 273. If the inverse fine structure constant is 137, then twice 137 minus 1 is exactly the number of degrees between absolute zero and the freezing point of water on a scale invented by a Swedish astronomer in 1742 for reasons that have nothing to do with quantum mechanics whatsoever. They had shown that Eddington's method could connect the strength of electromagnetism to an 18th century thermometer. It was published, which tells you something about how plausible the style of argument looked at the time. The editor, a man named Arnold Sommerfeld, worked out that he had been had and was furious. He demanded a retraction and got one. Bether, who was 24 years old and had not yet done any of the work that would eventually get him the Nobel Prize for explaining how stars burn, came close to real professional damage over it. There is an epilogue to that story that has nothing to do with physics, and I am going to tell it anyway. Arnold Sommerfeld had founded and edited Die Naturwissenschaften for 32 years. In 1935, he was removed from the editorship for being Jewish. In March of 1942, having been ordered to vacate his home ahead of deportation, he took his own life. He was 80 years old. The hoax paper is remembered as a charming anecdote about scientific self-policing. Almost nobody who repeats it knows what happened to the man who was angry about it. But Eddington did not stop. That is the part that is difficult to watch. He spent the last decade of his life on a project he called Fundamental Theory, an attempt to derive not just alpha, but the ratio of the proton mass to the electron mass, the number of particles in the observable universe, the cosmological constant, all of it, from pure algebra. He worked on it until he died on the 22nd of November, 1944, at the age of 61. The manuscript was unfinished. Cambridge University Press published it posthumously in 1946 under the title Fundamental Theory, edited into a form that could be printed by a colleague who had to reconstruct large parts of the argument from notes. Almost nobody has ever been able to follow it. The historian of science Hel Krag, who has read more of Eddington's late work than anyone alive, calls it a grand failure, and notes that the reason the physics community rejected it was not primarily the numerology. It was that Eddington was using quantum mechanics in a way that no quantum physicist recognized. Now here is the correction I actually want to make, because the version of this story that circulates is lazy and it makes the wrong lesson available. Eddington's argument was not numerology, not in the sense that people mean when they say numerology, which is the practice of looking for coincidences between numbers and assigning them meaning. Eddington did not go looking for a formula that spat out 136. He started from the Dirac equation, which was the deepest description of the electron available to anybody in 1929, and counted structural degrees of freedom in the algebra, which is a legitimate thing to do and a technique that is used constantly in modern theoretical physics. His starting point was real physics. His method was real mathematics. He collapsed into numerology at one specific moment, and the moment is identifiable to the sentence. It is the moment he decided the answer had to be a whole number, and that when the measurement disagreed with his whole number, the measurement had to be accommodated rather than obeyed. That is the failure, not the counting, the certainty. And that failure is the first serious attempt to answer the question we are chasing, and it is worth being clear about how it failed. Because it failed twice over. It failed on its own terms, because 137 is not the value. But it also failed in a way that made the underlying problem worse rather than better. And this is the pattern that repeats for the next 90 years. Because look at what the measurement actually says. The inverse fine structure constant is 137.035999 and change. That is not 137, but it is only about 0.02% away from it. That is close enough to ruin a career. If the value had come back as 137.4 or 136.8, nobody would have wasted a career on it. The tantalizing thing about alpha is that it sits just far enough from a clean integer to rule out every simple explanation, and just close enough to keep suggesting that a slightly less simple explanation might work. It is a lock that turns most of the way. Eddington heard the tumbler click and forced it. His reputation was still recovering when he died, and he never had the satisfaction of being told he was wrong for a reason he could have accepted. He simply became unfashionable, and then became a joke, and the joke was made by a man who would later calculate the fusion reactions that keep the sun alight. And if you think the lesson was absorbed, consider who did it next. Paul Dirac was among the people least impressed by Eddington's project. He is on record being dismissive of it. He had written the equation that Eddington was trying to count degrees of freedom in. He understood it better than its critic did, and he did not think you could extract the constants of nature by juggling matrix components. In 1937, Dirac published a 2-page letter in Nature called The Cosmological Constants. The argument starts with a ratio. Take a proton and an electron and ask how strongly they attract each other electrically compared to how strongly they attract each other gravitationally. Electromagnetism wins by an enormous factor. The number is around 2 times 10 to the 39th, 2 followed by 39 zeros. Then take a completely different ratio. Ask how old the universe is, expressed in the natural time unit you can build out of the electron's charge and mass and the speed of light, which is the rough time it takes light to cross an electron. That number is also somewhere around 10 to the 39th or 40th. 2 ratios, built from entirely unrelated physics, one from atomic and gravitational forces, and one from cosmology, landing on the same absurd magnitude. Dirac refused to accept that as an accident, and he drew the conclusion that follows if you take it seriously, which is a genuinely bold one. The age of the universe is not fixed, it increases. It is bigger today than it was yesterday. So if the 2 ratios are equal because they are connected, rather than because we happen to live at a convenient moment, then the other ratio has to increase too. And the only way for the ratio of electric to gravitational force to grow is for gravity to get weaker. Dirac proposed that the gravitational constant is not constant, that it decreases in inverse proportion to the age of the universe. That is the large numbers hypothesis, and I want to be clear that it is real physics. Proposed by the man who predicted antimatter in a real journal, and it made a testable prediction, which is more than most of the numerology in this story ever managed. It was tested. It failed. Edward Teller pointed out in 1948 that a stronger gravitational constant in the past means a hotter sun and a hotter Earth, and running the numbers backwards to the Cambrian gives you oceans that should have been near boiling at a time when the fossil record is full of animals that were demonstrably not boiled. The modern constraints are far more brutal. There are retroreflectors sitting on the surface of the moon, left there by the Apollo missions and by Soviet rovers, and for over 50 years people have been bouncing lasers off them and timing the return to a precision of a few centimeters over a distance of nearly 400,000 kilometers. If gravity were weakening, the moon's orbit would be spiraling outward at a rate that measurement would see immediately. It is not. The bound on any fractional change in the gravitational constant is now at the level of parts in 10 trillion per year, and Dirac's proposal requires something around 1/100th of a billionth per year. He was wrong by more than 3 orders of magnitude. Dirac was 35 when he proposed it. He was still defending versions of it in the 1970s, in his 70s. Long after the observational case against it had become overwhelming, I raise it not to embarrass a great physicist, but because it demolishes the comfortable reading of the Eddington story. It would be convenient to conclude that Eddington went numerological because he was old, or eccentric, or emotionally invested in a theological view of the universe, all of which have been said about him. But Dirac was none of those things. Dirac was the most austere, least sentimental theorist of his generation, a man whose colleagues joked about the unit of 1 word per hour, and he saw 2 enormous dimensionless numbers sitting near each other and could not accept that it meant nothing. The difference is instructive. Dirac's numbers were huge, and huge numbers plausibly connect to the age of the universe, which is also huge and which changes, so his coincidence had a mechanism available to it, and the mechanism made predictions, and the predictions were checked and killed. Alpha has none of that. It is not huge. It is a number a bit smaller than 1. It has no cosmic anchor, no obvious partner quantity, and as we are about to see, no measurable change over billions of years. There is nothing to attach a mechanism to. That is the whole difficulty, in 1 sentence. The large numbers hypothesis was wrong in a way that could be demonstrated. Alpha is not even wrong yet, because nobody has managed to be wrong about it in a way that could be checked, which would be enough of a cautionary tale on its own. But it did not stop anybody, because at the exact moment Eddington was adding 1, a man in Zurich with a mind so precise that his colleagues called him the conscience of physics, was arriving at the same obsession from the opposite direction entirely. He did not think the number could be derived from logic. He thought it might be coming from inside the person doing the deriving. Wolfgang Pauli was 21 years old when he wrote a 237-page review article on the theory of relativity for a German mathematical encyclopedia. Einstein read it and remarked that anyone studying it would not believe the author was 21, and that he did not know what to admire more, the psychological grasp of the development of the ideas, the sureness of the mathematics, the depth of the physical insight, or the clarity of the presentation. That was the opening move of his career. 4 years later, he formulated the exclusion principle, the rule that says no 2 electrons can occupy the same quantum state, which is the reason matter takes up space, the reason the periodic table has the shape it has, and the reason you do not fall through your chair. In 1930, faced with an apparent violation of energy conservation in beta decay, he proposed a particle that carried no charge, almost no mass, and interacted so weakly that he wrote in his own letter that he had done a terrible thing, because he had postulated a particle that could not be detected. It took until 1956 for anyone to detect it. It is called the neutrino, and about 100 trillion of them are passing through your body every second. He was also, by universal account, terrifying. Pauli's reputation among his colleagues was not for genius alone, but for a kind of surgical, unforgiving intolerance of sloppy thinking. He is the origin of the phrase that a bad piece of work is not even wrong, meaning it is so poorly formed that it cannot be evaluated at all. That attribution comes to us primarily through Rudolf Peierls, and I have never been able to find Pauli writing it down himself, so treat the wording as physics folklore rather than documented text. What is thoroughly documented is the behaviour. He would sit in seminars, shaking his head, muttering the German word for wrong, and colleagues who were themselves world-class physicists described the experience of presenting to him in the language people usually reserve for surgery. There was also the joke about the equipment. Physicists at Göttingen and Hamburg maintained, with the entirely straight faces of people who were pretending to joke. That experimental apparatus tended to fail when Pauli was nearby. Vacuum systems broke. Glassware shattered. Otto Stern, who ran one of the best experimental groups in Europe and would later win a Nobel Prize, is said to have banned Pauli from his laboratory. The most famous version of the story has a piece of equipment at Göttingen failing catastrophically at the exact moment Pauli's train was stopped at the station. I am telling you this as folklore, because that is what it is. There is no primary documentation for the train. But the fact that a generation of the most rigorous scientists on Earth thought it was funny to attribute quasi-magical properties to one specific man tells you something about the atmosphere around him, and it matters for what comes next, because Pauli did not entirely think it was a joke. In 1927, his mother died by suicide. She was a writer and a pacifist, and Pauli was close to her. His father remarried almost immediately to a woman his son could not stand. In 1929, Pauli married a cabaret dancer named Cather Deppner. She left him within a year for a chemist. There is a quotation attributed to him about this, that if it had been a bullfighter he could have understood it, but a chemist. And while I cannot verify the exact wording, everyone who knew him reports the tone was accurate. He began drinking, heavily and in public, in a way that produced arguments in bars and damaged his work. By 1931, the man who had been the most precise thinker in European physics was, by the accounts of the people around him, coming apart. His father, who was a physician, made a phone call to a colleague in Zurich. The colleague was Carl Gustav Jung. Jung took one look at the situation and did something clever and slightly cold. He did not analyse Pauli himself, not at first. He recognised that a mind like that would immediately start producing dreams tailored to what it thought the famous analyst wanted. So he handed him to a young trainee named Erna Rosenbaum, who had been in practice for a matter of months, with instructions to interfere as little as possible and let the material come out uncontaminated. It came out in a flood. Pauli recorded well over 1,000 dreams. Jung eventually used around 400 of them as the central case study of his book Psychology and Alchemy, published in 1944, where the dreamer is described anonymously as a young man of excellent scientific education. It was decades before it became widely known that the anonymous scientist in one of Jung's most important works was the man who discovered the exclusion principle. And in the middle of that material is the one Jung called the Great Vision, which Pauli experienced as an image of what he called the world clock, a three-dimensional structure with a vertical circle and a horizontal circle sharing a centre, rotating at rhythms with whole number ratios, carrying a black bird, the whole thing radiating a sense of what Pauli described as the most sublime harmony. Jung, who spent his career cataloguing this kind of imagery across cultures, considered it the single most remarkable mandala vision anyone had ever brought him. It is at this point that Pauli's relationship with the number begins, and the important thing is that it did not begin as mysticism. It began as a professional judgment. Pauli understood, more clearly than almost anyone alive, exactly what quantum mechanics could and could not deliver. He had built large parts of it. He knew where the theory got its numbers from. And he had concluded that the fine structure constant was structurally different from everything else in the theory, because everything else was either derived or definitional, and this was neither. He said so in the most formal setting available to a physicist. When he received the Nobel Prize, awarded in 1945 for the exclusion principle, he stated in his lecture that quantum mechanics could not be regarded as complete, and that the conclusion could only be written once there existed a theory that determined the value of the fine structure constant. That is the Nobel lecture. That is not a private letter or a late-night remark. He stood up in Stockholm and told the world that the theory he had helped to build had a hole in it, and pointed at the hole and said that nobody could close it. Nobody has closed it. 80 years later. What Pauli did next is the part that gets him laughed at, and I think the laughter is cheap. He began to wonder, seriously and in extensive written correspondence with Jung that ran for more than 20 years and has been published in full, whether the reason physics could not produce the number was that physics was the wrong tool. Not because physics is inadequate at physics. Because the act of understanding is not a physical process that physics has any account of. Pauli's suggestion, and he was careful about it, was that mind and matter might be two aspects of a single underlying reality, and that certain structures certain numbers might sit at the join, appearing simultaneously as features of the physical world and as features of the human unconscious. He thought 137 might be one of them, and this is where I have to correct something, because there is a claim about all this that has escaped into general circulation, and it is presented as though it means something. In Hebrew, the letters of the word Kabbalah carry numerical values, and if you add them, they sum to 137. That is true. It is not a hoax, and I am not going to pretend it is. It is a standard result in gematria, and it appears in the serious scholarly literature on Jewish mysticism. It also means nothing whatsoever, and the reason it means nothing is worth spelling out precisely, because it is the same reason every other numerological coincidence in this story dissolves the moment you look at it properly. There are tens of thousands of words in Hebrew. Each one produces a number. There are only a few hundred numbers in the range where interesting physical constants live. The chance that some spiritually significant word lands on any given 3-digit target is not small, it is close to certain. And the target itself was chosen after the fact, if the inverse fine structure constant had turned out to be 118. We would be reading essays about the word that sums to 118, and they would feel exactly as significant. Pauli, to his credit, was aware of this problem, and it did not fully satisfy him, which is interesting in itself. He was not looking for a coincidence to validate a belief. He was looking for a mechanism, and he never found one, and he knew he never found one. He died on the 15th of December, 1958, aged 58, of pancreatic cancer that had been diagnosed only days earlier. The account of the room number comes from Charles Enns, who was his assistant at the time, was physically present, and published it in his biography of Pauli in 2002. Enns elsewhere described the coincidence with the word Kabbalistic, which is either a pointed choice or an unconscious one, and I have never been able to decide which. So the story is not apocryphal, it is first-hand from a named eyewitness in a book from a university press. But it is also, and this is the part people skip, exactly the kind of coincidence that Pauli spent 30 years arguing might not be a coincidence happening to Pauli on the last day, which is either the universe making a joke in extremely poor taste, or, far more likely, the reason we all remember this particular hospital room out of the many thousands of rooms that physicists have died in. Both of the first two attempts on the number are now on the table, and both are failures, and they failed in opposite directions. Eddington tried to derive it from the structure of mathematics and produced an integer that reality refused to confirm. Pauli tried to locate it at the boundary between mind and matter and produced a lifetime of correspondence and no equation. One of them was too confident, the other was too honest to fake a result. Neither of them got anywhere near it. And you could look at that and conclude that the problem was the two men, that they were working before the tools existed, that they were reaching for something in the dark that a later generation with better instruments would simply walk up to and read off a dial. That generation arrived. They built the instruments. The instruments are, without exaggeration, the most precise measuring devices that human beings have ever constructed for any purpose. And what those instruments found is so much worse. In 1928, Dirac's equation made a prediction about the electron that was clean, unambiguous, and had no adjustable parameters in it at all. An electron behaves like a tiny magnet, and the strength of that magnetism relative to its spin is given by a quantity physicists call G. Dirac's theory said G equals 2. Exactly 2, not approximately. The number falls out of the structure of the equation with nothing left over. In 1947, Polycarp Cush and Henry Foley at Columbia measured it, and it was not 2. It was 2.0023 and change, about 1 part in 1,000 too big. Within months, Julian Schwinger worked out where the excess came from. An electron is never alone. It is constantly emitting and reabsorbing photons, and each of those photons drags the magnetism slightly. Schwinger calculated the leading correction and got a beautifully simple answer. The excess is alpha divided by 2 pi. He was so pleased with it that the symbol is carved on his gravestone in Mount Auburn Cemetery in Cambridge, Massachusetts, alpha over 2 pi. A man's entire life reduced to the smallest correction term in quantum electrodynamics, and he chose it himself. That correction is the doorway. Because the deviation of g from 2 is built out of alpha, if you can measure the deviation precisely enough, and if you can calculate the theoretical expression precisely enough, you can run the logic backwards and extract alpha to a precision no spectroscope could ever reach. Both halves of that turned out to be brutally hard, and the story of each half is the story of a career. Start with the measurement. The apparatus is called a Penning trap, and what Gerald Gabriels's group at Harvard built over about 3 decades is arguably the most refined instrument in the history of experimental physics. They take 1 electron, not a beam, not a gas. A single electron, held in place by a combination of magnetic and electric fields inside a cavity made of silver, cooled to about 1/10 of 1 degree above absolute zero, and hung in a vacuum better than the vacuum of interplanetary space. They keep it there for months. The same electron. They give it a name. And they measure 2 frequencies, the rate at which it circles in the magnetic field and the rate at which its spin precesses, and the tiny difference between those 2 frequencies is the whole game. In 2008, the Harvard group published a value that stood as the most precise measurement of any property of an elementary particle for 14 years. In February of 2023, in Physical Review Letters, volume 130, article number 071801, Singfan, Thomas Myers, Bingji Sukra and Gabriels published the improvement. They pinned the electron magnetic moment to an uncertainty of about 0.13 parts per trillion. I want to make that number physical because parts per trillion is not a quantity that human intuition handles. The moon is on average about 384,000 kilometers away. If you measured that distance to a precision of 0.13 parts per trillion, your uncertainty would be about 50 micrometers, roughly the width of a human hair. That is the accuracy with which we know the magnetism of a single electron. Now the other half. To turn that into alpha, you need the theoretical expression, and the theoretical expression is an infinite series. Each term corresponds to a more complicated way for the electron to interact with the vacuum around it, and each term requires you to enumerate and evaluate every Feynman diagram at that level of complexity. The first term, Schwinger's, is 1 diagram, the second is 7, the third is 72, the fourth is 891, the fifth, which is the 10th order in the coupling, is 12,672 Feynman diagrams. 12,672 separate integrals, most of them not solvable in closed form, requiring numerical evaluation on supercomputers with error control tight enough that the accumulated uncertainty stays below the experimental precision. That calculation was carried out over decades, principally by Toichiro Kinoshita, working with Tatsumi Aoyama, Masashi Hayakawa, and Makiko Neo. Kinoshita began working on the electron magnetic moment in the 1960s and was still publishing on it in his 90s. It is one of the longest sustained calculations in the history of science, and the published result in Physical Review D in 2018 represents the labour of most of a human lifetime. Here is what happened to it. In 2024, a re-evaluation of one class of those 10th order diagrams disagreed with the earlier evaluation, not by a rounding error. The 2 independent calculations of the same quantity differed by roughly 5 standard deviations, which in physics is the threshold at which you are permitted to announce a discovery. Except this was not a discovery. It was 2 groups of extremely careful people getting different answers to the same arithmetic. It took a further independent recomputation, published in Physical Review D in early 2025, to sort out which was right and restore agreement. I want to sit on that for a second, because it is a small thing that tells you something large, the single most precisely tested prediction in all of science, the crown jewel that gets cited every time someone wants to argue that quantum electrodynamics is the most successful theory ever devised, was internally inconsistent at 5 sigma for a period of months, and the resolution required going back into a set of 12,000 integrals to find the discrepancy. Nobody was hiding it. It was published openly, which is exactly how it should work. But you did not hear about it, and there were no headlines, and the phrase most successful theory in the history of physics continued to be used without qualification the entire time. When the dust settled, the electron magnetic moment gave a value for the inverse fine structure constant of 137.03 5999166, with an uncertainty of 15 in the last 2 digits. That is a precision of about 1/10 of 1 part per billion. And now I have to tell you the thing that makes this whole edifice more fragile than it looks. And it is the reason the story does not end here with everyone shaking hands. That number is not a measurement of alpha. It is a measurement of the electron's magnetism, converted into alpha by assuming that the theoretical expression is complete. Which means it assumes that the only things contributing to the electron's magnetic moment are the particles and forces we already know about. If there is anything else out there, any undiscovered particle light enough or coupled strongly enough to nudge the electron's magnetism at the 12th decimal place, then the conversion is contaminated, and the alpha you extract is wrong by exactly the amount of new physics you fail to account for. Which means you cannot use the electron magnetic moment to test the standard model. Not on its own. To do that, you need alpha from somewhere else, measured in a way that does not lean on the theory you are trying to test. Then you feed that independent alpha into the theoretical expression, predict what the electron's magnetism should be, compare it to the Harvard number, and any difference is a signal that something unknown is out there. That comparison is one of the sharpest tools in all of particle physics. It is sensitive to physics at energy scales that no accelerator on Earth can reach directly. Whole categories of proposed dark sector particles live or die on it. And it has been broken since 2020. Because the 2 independent measurements of alpha, the 2 experiments built specifically to provide the clean external number that makes the whole test possible, disagree with each other. Not slightly. Not within the error bars, where a bit of hand-waving would smooth it over. They disagree by more than 5 standard deviations, and they have been disagreeing for 6 years, and nobody knows why. There is a second way to get at alpha, and it is beautiful, and it has nothing to do with magnetism. The trick is to make an atom absorb a photon and watch it flinch. When an atom absorbs light, the photon transfers momentum and the atom recoils. The size of that recoil depends on the mass of the atom and on Planck's constant. If you can measure the recoil velocity precisely enough, you get the ratio of Planck's constant to the atomic mass. Combine that with the Rydberg constant, which is known to about 1 part in a trillion from hydrogen spectroscopy, and the mass of the atom relative to the electron, which is known from trapping single ions in magnetic fields, and alpha falls out of the arithmetic. Nothing in that chain depends on quantum electrodynamics being correct. No Feynman diagrams. No assumption that we have found all the particles. It is atomic physics and arithmetic, and that is precisely what makes it valuable. It is the clean number, the independent one, the one you can use as a control. 2 groups in the world can do this at the required precision. The first is at the University of California, Berkeley, led by Holger Miller. They work with cesium. Their atom interferometer drops a cloud of cesium atoms, splits each atom's wave function into 2 paths using laser pulses, kicks one path with a series of momentum transfers, and then recombines them and reads the interference fringes. The number of photon kicks they can apply before the coherence dies determines the precision, and they got it up into the hundreds. In April of 2018, in the journal Science, volume 360, pages 191 to 195, Richard Parker, Chenghui Yu, Weqing Zhong, Brian Esty and Miller published their result. The inverse fine structure constant, they reported, is 137.035 999046, with an uncertainty of 27 in the final two digits. That is a precision of about 0.2 parts per billion, and at the time it was the most accurate determination of alpha ever made by any method. The paper's title says exactly what they thought they were doing. Measurement of the fine structure constant as a test of the standard model. They had built the control. The second group is in Paris, at the Laboratoire Castles-Brossel, led by Sada Guayati-Khalifa. They work with rubidium, and they use a slightly different technique, holding the atoms in a standing wave of laser light and driving them through what are called block oscillations to accumulate momentum kicks by the thousand. In December of 2020, in Nature, volume 588, pages 61 to 65, Lowe Morel, Gibaniao, Pierre Clad and Guayati-Khalifa published their number. 137.035999206, with an uncertainty of 11 in the final two digits. 81 parts per trillion. 2.5 times better than Berkeley. Put those two numbers side by side. Berkeley says 046. Paris says 206. They differ in the 10th significant figure by 160 units, and the combined uncertainty of the two experiments is about 29 units. That is a disagreement of more than 5 standard deviations. The figure usually quoted in the literature is 5.4. The Nature paper itself states it plainly in the abstract, which is not something you do lightly. The authors of the most precise measurement of the fine structure constant in human history chose to announce, in the first paragraph, that their result was irreconcilable with the previous best result. Let me make the size of the disagreement concrete. Because 5 sigma sounds abstract, and 1.2 parts per billion sounds like nothing, the Earth is about 150 million kilometers from the Sun. If two teams measured that distance with the relative precision these experiments claim, and disagreed by the amount they disagree about alpha, their answers would differ by about 180 meters. Now, on a scale of 150 million kilometers, 180 meters is nothing. That is the point. The disagreement is not large, it is minuscule. But both teams have quoted uncertainties much smaller than that, which means both teams are claiming to know the answer to within a few tens of meters. They cannot both be right. It is arithmetically impossible. One of these experiments, and possibly both, contains an error that its own team, working for years with the most sophisticated apparatus in atomic physics, has been unable to find. The obvious question is whether the difference comes from the atoms. Cesium and rubidium are different elements with different masses and different internal structure. Maybe something about one of them behaves in a way nobody modelled. Pierre Clad, one of the authors of the Paris result, addressed this directly in an interview at the time of publication. He said he did not think the discrepancy came down to the choice of cesium versus rubidium, that something in one of the two experiments most likely has not been properly accounted for, and that understanding what is now the task. That was the end of 2020. It is now the middle of 2026. Neither group has published a new determination of alpha. Both are rebuilding. Both have talked at conferences about systematic effects they are hunting, laser wavefront distortions, gravity gradients, the way the phase of a laser beam varies across its profile in ways that shift the interferometer by a few parts in 10 billion. Both expect improvements. Nobody has published a resolution. 6 years. The two cleanest measurements of the most fundamental number in physics have been staring at each other across an unbridgeable gap for 6 years, and the field has essentially learnt to live with it. Which brings me to what the international body responsible for the constants of nature had to do about it and I want to describe this precisely, because it is one of those moments where you can see the machinery of science working exactly as designed, and it is still uncomfortable to watch. Every 4 years, a committee produces the official recommended values of the fundamental physical constants. It is called the Task Group on Fundamental Constants, operating under the Committee on Data of the International Science Council. The numbers they publish are what goes in the textbooks, what goes in the software libraries, what everyone uses. The 2022 adjustment was published in Reviews of Modern Physics in 2025. Their job is to take all the world's measurements of a quantity and combine them into a single best estimate with a single uncertainty. That works fine when the measurements agree. When they disagree by 5 sigma, it does not work at all. Because a standard statistical combination of 2 irreconcilable numbers produces an answer that is precise, confident, and almost certainly wrong. So they did what metrologists do in this situation. They applied an expansion factor. They multiplied the quoted uncertainties on the input measurements of alpha by 2.5, until the disagreement was diluted enough that every input sat within 2 of the expanded standard deviations of the combined result. Then they published the combined result. That is the official value of the fine structure constant, 137.035,999,177, with an uncertainty that has been deliberately inflated by a factor of 2.5 because the underlying data is in a state of open conflict. I want to be fair here. This is not fraud, and it is not a cover-up. The expansion factor is documented in the paper, in the tables, in the text. It is standard practice in metrology, and there is a reasonable argument that it is the most honest thing you can do when you know your inputs are inconsistent and you do not know which one is wrong. Publishing a tight uncertainty you do not believe in would be worse. But strip the technical language off and look at what it actually is. The most fundamental dimensionless number in physics, the number Feynman put on his wall, the number Pauli said quantum mechanics could not be finished without, currently has an official value that was arrived at by widening the error bars until the contradiction disappeared. That is not a measurement. That is a settlement. And the consequence is not academic. The whole point of the recoil experiments was to provide an independent alpha so that the electromagnetic moment could be used to hunt for new physics. Run that comparison using the Berkeley number, and the electron's magnetism comes out on one side of the standard model prediction. Run it using the Paris number, and it comes out on the other side. The sign of the anomaly flips. Whether there is undiscovered physics hiding in the electron depends entirely on which of 2 laboratories you decide to believe. That is where the search for physics beyond the standard model in the electron sector currently sits, not blocked by a lack of precision, blocked by an excess of it, delivered by 2 experiments that cannot both be telling the truth. I want to say something about what that is like, because it gets lost in the language of standard deviations. There are perhaps a few dozen people on Earth qualified to run one of these experiments. They have spent, in most cases, their entire adult lives on a single apparatus. The Berkeley interferometer and the Paris interferometer are not devices you buy. They are devices you spend a decade building and then another decade understanding, and the understanding is the hard part, because at these precisions the enemy is not noise, it is the possibility that a laser beam is very slightly not flat, or that the local gravitational gradient in the building shifts the atoms by a fraction of a wavelength, or that some effect nobody has thought of yet is contributing at the level of 1 part in 10 billion. Both teams have now spent 6 years hunting for an error that one of them almost certainly has, and neither of them can find. That is not a failure of care. It is what happens when you push measurement to the point where the apparatus starts telling you about itself as loudly as it tells you about the world. And I keep coming back to the fact that this is not obscure. This is the fine structure constant. This is the number Feynman said good theorists put on their wall. 2 of the best laboratories in the world produced irreconcilable values for it. In Science and in Nature, the 2 highest profile journals in existence, and the international committee responsible for the constants of nature had to inflate the error bars to paper over it, and the resulting situation has persisted for 6 years without resolution. Try to imagine any other field where 2 flagship results contradict each other at 5 sigma for 6 years, and the general public hears nothing about it. You already know why. It is not suppression, and it is not a conspiracy. It is that the disagreement is in the 10th decimal place, and there is no way to make the 10th decimal place feel like news. And so a genuine unresolved contradiction at the foundation of physics sits in the literature being politely managed by 300 specialists, while everyone else goes on quoting 1/137. And there is a caveat sitting underneath every single number I have just given you, printed in every one of these papers, that nobody outside the field ever hears about. Because it is technical and boring, and it happens to be the most important thing in this entire story. All of these values are quoted at 0 momentum transfer, which is a way of saying that they only apply if you do not look too hard. Empty space is not empty. That sentence has been said so many times in popular science that it has lost all of its force. So let me say the operational version instead, the one with consequences. Take an electron and put it alone in a perfect vacuum. Around it, continuously, pairs of virtual particles are flickering into existence and annihilating, borrowing energy from nothing and paying it back within the window that the uncertainty principle allows. Among those pairs are electrons and positrons. The electron carries negative charge and the positron carries positive charge, and they respond to the field of the real electron sitting in the middle of them. The positrons are attracted. The virtual electrons are repelled, which means the cloud of virtual pairs orients itself. Positive ends inward, negative ends outward. The vacuum polarizes. And a polarized medium screens charge. It is exactly what happens when you put a charge inside a dielectric, except the dielectric here is the structure of empty space itself. So when you stand back and measure the charge of an electron from a distance, you are not measuring the electron's charge, you are measuring what is left of it after the vacuum has taken a cut. Get closer, and you penetrate deeper into the polarized cloud, and there is less screening material between you and the source, and the charge you measure goes up. Closer still, and it goes up more. In the language of particle physics, getting closer means colliding at higher energy, so the statement is that the electromagnetic coupling increases with energy. This is not a speculation, and it is not an interpretation. It has been measured. At the energies of ordinary life, the energies at which chemistry happens and atoms hold together and photons come off the surface of the sun, the inverse fine structure constant is 137.036. That is the value on Feynman's wall. At the mass of the Z boson, about 91.2 billion electron volts, which is the energy regime that the Large Electron-Positron Collider at CERN spent 11 years exploring, the same quantity is not 137. It is 128.962, plus or minus about 3 in the last 2 digits. Electromagnetism is roughly 6% stronger up there. Not because anything changed, because you are looking closer and the vacuum is hiding less of the charge from you. I want to be careful that this lands correctly, because there are 2 wrong conclusions available and both of them are popular. The first wrong conclusion is that this makes the mystery worse in a mystical way, that the constants are somehow alive or shifting or unreliable. They are not. The running of the coupling is one of the most rigorously understood processes in quantum field theory. It is calculable, it was predicted before it was measured, and the measurements at LEP confirmed it to high precision by studying how electrons and positrons scatter off each other at different energies. This is settled physics, and there is nothing spooky in it. The second wrong conclusion is the one I actually want to take apart, because it is the standard move that professional physicists make when someone asks them about 137, and I think it is a dodge. The move goes like this. 137 is not fundamental. It is the value of a scale-dependent quantity at one particular arbitrary low energy point. There is nothing special about that point, except that it happens to be where we live. Therefore, asking why the constant is 137 is a naive question, like asking why the temperature outside is 18 degrees. You are mistaking a local reading for a law. Every word of that is true, and it does not help at all. Here is why. The running of the coupling is a function. If you know the value at one energy, the mathematics gives you the value at every other energy. The function itself contains no free numbers. It is determined by the charges and masses of every particle in the theory, which means the whole curve is fixed once you nail down a single point on it. So you have not eliminated a free parameter, you have relabeled it. You can stop asking why the coupling is 1/137 at zero energy and start asking why it is 1/129 at the mass of the Z boson, and you will find that nobody can answer that either, and for exactly the same reason. The mystery is not attached to the number 137. The mystery is attached to the curve, and the curve needs one number. From outside, forever, the people who tell you that the running dissolves the puzzle are correct that the specific digits are an artifact of our altitude. They are wrong that this makes the puzzle smaller. It makes it harder to point at, which is not the same thing. And there is something else in the running that almost nobody mentions, and when I understood it properly, it changed how I think about the number entirely. The steepness of the curve depends on what is in the vacuum. Every charged particle that exists contributes to the screening. Electrons contribute. Muons contribute. Quarks contribute. If there is some charged particle out there that we have not discovered, with a mass low enough to matter, it is already contributing, right now, and has been since the beginning. Which means the value 137.036 is not a bare fact about electromagnetism. It is the accumulated result of every charged thing that exists in the universe. Integrated across all the energies below us, summed and screened and delivered to us as a single number at the bottom of the ladder. The number is a census. It is the universe reporting, in one figure, the total inventory of everything that carries charge. And when you extract alpha from an atomic recoil experiment in Paris, what you are actually doing is asking the vacuum to tell you what is in it, and the vacuum answers in a number that arrives with no breakdown, no itemization, and no explanation of how the total was reached. I said earlier that the number on Feynman's wall was already out of date the moment he wrote it. This is what I meant. Not that it drifts, that it was never the constant. It was the reading at the depth we happened to be standing at, produced by a process of concealment that operates everywhere and always, and the true value at the bottom of the cloud, the actual charge on the actual electron with no screening at all, is not 137 and not 129. Follow the curve up. The coupling keeps rising, faster and faster, because the stronger it gets, the more pairs it produces, and the more pairs it produces, the faster it gets stronger. The curve is not linear, it runs away, and at a finite energy, it becomes infinite. That point has a name. It is called the Landau pole, and the energy at which it occurs is so far beyond anything physical that writing it down is almost a joke. Something like 10 to the power of 277 electron volts, which exceeds the total energy content of the observable universe by an amount for which there is no useful comparison. Lev Landau worked this out in 1954 with Alexei Abrikosov and Isaac Kalatnikov, and he drew the obvious conclusion, which was that quantum electrodynamics is not a complete theory. It contains, in its own structure, the seed of its own breakdown. Push it hard enough, and it does not merely become difficult to calculate with. It becomes meaningless. Landau took this seriously enough that he spent part of the 1950s arguing that quantum field theory as a whole was finished as a framework, and he moved on. He was wrong about the general case as it turned out. The strong nuclear force runs the other way, getting weaker at high energy rather than stronger, a discovery that won a Nobel Prize in 2004. But he was not wrong about electromagnetism. Taken on its own terms, taken seriously to arbitrarily high energy, quantum electrodynamics destroys itself. Landau himself did not get to see any of the resolution. In January of 1962, driving on an icy road outside Moscow, his car collided with a truck. He suffered massive injuries. Soviet physicists mobilized on a scale that has few parallels in the history of science, flying in specialists from across Europe, chartering aircraft for medicine, keeping a rota of volunteers at the hospital. He was clinically dead more than once, and was revived. He survived for 6 more years. He never did physics again. The man who could hold the entire structure of theoretical physics in his head could no longer follow an argument. He died in 1968, and this was the same man who in 1938 had been arrested by the secret police and held in the Lubyanka for a year on a charge of comparing Stalinism to fascism, released only because Pyotr Kapitsa wrote directly to the Kremlin and offered his own personal guarantee. Landau later said the year in prison had left him unable to work properly for a long time afterwards. 2 thefts from the same mind, 24 years apart, and the second one took everything. The situation he identified is still there. The theory that gives us the 12 decimal places, the theory that describes light and matter better than any description of anything ever produced by human beings, contains a mathematical statement that it cannot be the final answer. The coupling constant that is its only real input runs away to infinity if you follow it far enough. So the number is not fundamental, the theory that houses the number is not final, and the value we quote is a screened reading taken at one arbitrary depth by creatures made of the very charged matter doing the screening. You would think that at this point, somebody would at least be able to tell us whether the number has always had the value it has now. They have tried, and that story involves a natural nuclear reactor that switched itself on 2 billion years ago in what is now Gabon, and one of the most spectacular collapses of a scientific claim in the last 30 years. In 1972, at a uranium enrichment facility at Pirilat in southern France, a routine mass spectrometry check on a batch of ore came back wrong. Natural uranium anywhere on Earth, in any rock from any mine, contains the fissile isotope uranium-235 at a concentration of 0.7202%. This is one of the most reliable numbers in geochemistry. It is the same on the Moon. It is the same in meteorites. The isotope decays at a fixed rate, so the ratio depends only on time. And everything in the solar system started at the same time. The sample read 0.7171%. The discrepancy is 3 parts in 10,000. It is small enough that a less careful laboratory would have logged it as instrument error. The French logged it as a missing quantity of uranium-235 and started a security investigation. Because a shortfall in fissile material has an obvious and alarming explanation. The ore had come from a mine at Oklo in Gabon. When they went and looked, what they found was not theft. About 1.7 billion years ago, in a seam of uranium ore rich enough and wet enough, the neutron economy tipped over. Groundwater percolating through the deposit slowed neutrons enough to sustain fission. The deposit went critical. It heated up, boiled the water away, lost its moderator and shut down. When it cooled, water seeped back in and it started again. It cycled like that, roughly 3 hours on and 2.5 hours off, for a period on the order of hundreds of thousands of years. There were at least 16 separate reactor zones. A natural nuclear reactor built by nobody running on a duty cycle 2 billion years before anyone thought of it. The missing uranium-235 had been burned. Now here is why a physicist should care about that, and it is not the geology. A nuclear reactor is a laboratory. It is an extremely well-characterized laboratory, because the physics of neutron capture is understood in exquisite detail, and the products are still sitting in the rock, and one of those products is samarium. Samarium-149 has a neutron capture resonance sitting at about 0.1 electron volts. That is an absurdly low energy for a nuclear process. The reason it sits there is a near cancellation between the nuclear binding energy, which is measured in millions of electron volts, and the electromagnetic repulsion of the protons, which is also measured in millions of electron volts. Two enormous numbers subtracting to leave a tiny remainder, which means the position of that resonance is a magnifying glass. Nudge the electromagnetic contribution by 1 part in 10 million, and the resonance energy moves by a fraction of itself that is around 100 million times larger. Alexander Reactor spotted this in 1976 and published it in Nature. If the fine structure constant had been even slightly different 1.7 billion years ago, the resonance would have sat somewhere else. Samarium-149 would have absorbed neutrons at a different rate, and the isotope ratios preserved in the Oklo rock would not look the way they look. They look exactly the way they should if nothing changed. The definitive analysis came in 1996 from Thibault Damour and Freeman Dyson, published in Nuclear Physics B, volume 480. They worked through the reactor conditions, the neutron spectrum, the temperature, and put a bound on how much alpha could have changed in the intervening 1.7 billion years. Their answer, at 95% confidence, was that the fractional change was somewhere between minus 0.9 and plus 1.2 parts in 10 million. Over 1.7 billion years. That works out to a drift of less than about 5 parts in 10,000 trillion per year. From a rock. Later work, particularly a reanalysis by Petrov and colleagues in Physical Review C in 2006 using modern neutron transport simulation, refined the reactor modelling and did not overturn the conclusion. There is genuine disagreement in the literature about the details, because every Oklo bound depends on reconstructing the conditions inside a reactor that shut down before multicellular life existed, and on assuming that nothing else changed at the same time in a compensating way. Those are real caveats. But the headline survives. 2 billion years ago, in what is now Gabon, electromagnetism had the strength it has today, and then the astronomers said they had found it changing. The method is called many multiplet analysis, and it is genuinely clever. Different atomic transitions in different ions depend on alpha in different ways. Some strongly, some weakly, some with the opposite sign. If you look at light from a distant quasar passing through an intervening gas cloud, the cloud imprints absorption lines. If alpha was different in that cloud, the lines shift relative to each other in a specific predictable pattern that cannot be mimicked by the cloud simply moving. John Webb, Victor Flambaum, Michael Murphy and Vladimir Dzuba, working mostly out of the University of New South Wales, developed the technique and applied it to data from the Keck telescope in Hawaii, publishing in Physical Review Letters in 1999. They found a shift. Alpha appeared to have been smaller in the early universe by about 6 parts per million. That should have been the story of the decade, and it was treated with appropriate suspicion, which is the correct scientific response to a claim that a constant is not constant. The obvious test was to look at a different part of the sky with a different telescope. They did. The Very Large Telescope in Chile, looking mostly at the southern sky, gave a result of about plus 2 parts per million. Different sign, and in 2011, Webb and colleagues published the interpretation that made this famous. If alpha was smaller in the direction Keck looks, and larger in the direction the Very Large Telescope looks, then the variation is not in time. It is in space. A gradient, a dipole across the sky, with the universe having slightly stronger electromagnetism in one direction and slightly weaker in the other, and our galaxy sitting close to the neutral line. The claimed significance was around 4 standard deviations. It got called the Australian dipole. It generated an enormous amount of theoretical work, because a spatial gradient in a fundamental constant would mean the constant is a field, and a field has dynamics, and dynamics can be written down. Then, in 2015, in the monthly notices of the Royal Astronomical Society, volume 447, Jonathan Whitmore and Michael Murphy published a paper that took the whole thing apart. They had gone back and checked the wavelength calibration of the spectrographs, not the physics, the rulers. And they found that both instruments, the one in Hawaii and the one in Chile, suffered from long-range distortions in their wavelength scales. Gradients of order 200 meters per second across every 1,000 angstroms of spectrum, systematic, ubiquitous, present in essentially every observation. Those distortions are more than large enough to produce the apparent shifts in alpha. The signal was, to a large extent, the telescopes. I want you to notice something about that paper, because it cuts directly against the story I have been building, and I am not going to pretend otherwise. Michael Murphy was a co-author on the original detection. He spent years of his career on the claim that alpha varies, and he is the man who led the analysis that dismantled it and published it himself in a major journal with his own name on both sides of the argument. That happened. It is worth saying out loud, because this whole story has a lot of institutional failure in it, and it would be dishonest to leave out the one part where the system worked exactly as it is supposed to. Newer instruments have not revived the signal. The espresso spectrograph on the Very Large Telescope, built specifically with the calibration stability that the earlier work lacked, has looked at the same kind of systems and found results consistent with no variation at all. Meanwhile, back on Earth, the clocks got absurd. If alpha were drifting today, atomic clocks based on different transitions would drift relative to each other, because different transitions depend on alpha differently. Compare two clocks for a decade and you get a bound. In 2008, a group at the National Institute of Standards and Technology compared an aluminium ion clock to a mercury ion clock for about a year, and bounded the fractional drift of alpha at around 2 parts in 100 million trillion per year. The current best comes from comparing two different transitions in a single ytterbium ion at the German National Metrology Institute, using frequency ratio data spanning more than a decade. The answer is a drift of about 1.8 parts in 10 billion per year, with an uncertainty of 2.5 in the same units. Which is to say, consistent with zero and bounded so tightly that if alpha were drifting at the maximum rate still permitted, it would have changed by roughly 2 parts per billion across the entire 13.8 billion year history of the universe. So the question was, has this number always been this number? And the answer, from a natural reactor in Gabon, from gas clouds 11 billion light years away, and from ytterbium ions in a trap in Braunschweig, is yes. As far as anyone can measure, it has been this number everywhere and always. That sounds like reassurance. It is the opposite of reassurance, and I want to make sure the reason is clear, because it took me an embarrassingly long time to see it. A constant that varies is a physical thing. If alpha were drifting, it would be a field, and fields obey equations, and an equation is an explanation. You would be able to ask what the field is doing, what it couples to, what set its initial condition, why it is rolling in the direction it is rolling. There would be a mechanism, and mechanisms can be understood. A constant that never moves has no mechanism. There is nothing to ask. It is not doing anything. It has no history, no dynamics, no cause, and no story. It is a value that reality was apparently issued with and has never once revised. Every attempt to find the number moving has failed, and each failure has removed one more way in which the number could have been the kind of thing that has an explanation. There is exactly one place in all of physics where the integer 137 appears as a structural feature rather than as a measured value, and almost nobody who repeats the mystique of the number knows about it. Take the Dirac equation and solve it for an electron bound to a nucleus of charge Z, treating the nucleus as a point. The energy of the innermost electron comes out with a square root in it, and inside that square root is 1 minus the quantity Z times alpha, squared, now increase Z. Add protons. As long as Z times alpha is less than 1, everything is fine. but alpha is 1 over 137.036, so z times alpha reaches 1 when z reaches 137. Past that, the square root of a negative number. The energy of the ground state electron becomes imaginary. The equation does not merely predict something strange, it stops producing an answer at all. Element 137, therefore, cannot exist. This has been known since the 1930s, and it acquired a nickname. Some physicists call the hypothetical element Feynmanium, and there is a persistent claim, repeated in a great many places, that this is the reason the periodic table has a hard ceiling. It is wrong, and the reason it is wrong is the most instructive thing in this section. The catastrophe is an artifact of treating the nucleus as a mathematical point. Real nuclei have a size. A nucleus with 137 protons would be a few femtometers across, and once you spread the charge over a finite volume rather than concentrating it at a point, the singularity in the equation goes away. The electron sitting at the center of the nucleus does not experience an infinite field, because most of the charge is outside it. Work through the finite size calculation properly, which was done independently by Semyon Gerstein and Yakov Zeldovich in the Soviet Union, and by Walter Greiner's group in Frankfurt, and the energy levels continue smoothly straight through 137. Nothing happens there. Nothing at all. Something does happen. It happens later, somewhere around Z equal to 170, or 173 depending on the nuclear model you use. The innermost electron level does not go imaginary. It dives. It sinks all the way down and touches the negative energy continuum, the sea of states that Dirac's theory identifies with antimatter. And when a bound state reaches the negative energy continuum, the vacuum becomes unstable. It becomes energetically favourable for the vacuum itself to produce an electron and a positron out of nothing. The electron falls into the vacant innermost orbital of the nucleus. The positron is ejected and flies away. Empty space, sitting near a sufficiently charged nucleus, spontaneously manufactures matter and spits out the antimatter half. That is a genuine prediction of quantum electrodynamics in strong fields. It has never been observed, and people have been trying since the 1970s by smashing uranium nuclei into each other at Darmstadt to briefly assemble a combined charge of 184. There was a period in the 1980s when they thought they had seen it, sharp positron lines appearing in the collision debris, and it caused a great deal of excitement before better experiments showed the lines were not real. So the one place in physics where the number 137 appears as an exact integer is a place where the number is an artifact of an idealization that does not describe anything. The mystique found its one hard mathematical anchor, and the anchor was made of paper. But the question underneath it is real, and it survives the correction intact. What actually happens if you change the number? The answer is that you do not get a slightly different universe. You get one without chemistry in it, or one without stars, and the tightest constraint of all comes from a single nuclear energy level that a British astronomer talked himself into believing in because he was alive. In 1953, Fred Hoyle was at Caltech, and he had a problem. He was trying to explain where the elements come from, and he could not get past helium. To build carbon, you need 3 helium nuclei to fuse. 2 of them make beryllium-8, which is so unstable it falls apart in about 1/10 of a femtosecond, so the 3rd helium has to arrive during that window. The probability of that is vanishingly small unless the reaction is resonant, meaning the combined energy of beryllium-8 plus helium-4 happens to land almost exactly on an existing excited state of carbon-12. No such state was known. Hoyle reasoned that it had to be there anyway, because carbon exists, because he was made of it, and because there was no other route. He calculated where it had to sit, at an excitation energy of about 7.65 million electron volts, and he walked into William Fowler's laboratory and told a group of experimental nuclear physicists to go and look for it. They thought he was wasting their time. They looked anyway. It was there, within a fraction of a percent of where he said. The Nobel Prize for the theory of stellar nucleosynthesis was awarded in 1983. It went to William Fowler. Hoyle was not included. The omission is one of the more openly discussed injustices in the history of the prize, and the usual explanation is that Hoyle had spent the intervening years being loudly, publicly wrong about several other things, and had made enemies on the committee. Here is why that resonance matters for our number. The position of the Hoyle state is another one of those near cancellations. The nuclear force wants to bind the 12 nucleons in carbon tightly. The electromagnetic repulsion between the 6 protons pushes the other way. The excited state sits where it sits because those 2 enormous effects nearly balance, and the leftover is the resonance energy. Change alpha, and you change the electromagnetic side of the balance, and the resonance moves. In 2000, Heinz Oberhammer, Attila Kutzt, and Helmut Schlattel published the calculation in Science, volume 289. They varied the strong force and the electromagnetic force in stellar models and tracked what came out. Their conclusion was that a change of about 0.5% in the strong force, or about 4% in the electromagnetic force, is enough to reduce the production of carbon or oxygen in stars by factors between 30 and 1,000. 4%, that is the width of the window, on that calculation. Now, I promised you I would be honest about contested results, and this one is contested. Later work using more sophisticated nuclear theory, including lattice calculations built on the effective field theory of the strong interaction by Evgeny Eppelbaum and collaborators, and separate analyses by Fred Adams and Evan Groves, has argued that the sensitivity is real but softer than the original claim, and that carbon production degrades more gracefully than the earlier numbers suggested. The window may be wider than 4%. It is not wide. What is not contested is the direction of the effect and the fact that a window exists. Turn alpha up far enough and the repulsion between protons wins. Heavy nuclei stop being stable and the periodic table collapses to its first few rows. Turn it down and chemical bonds weaken until molecules cannot hold structure at ordinary temperatures. Somewhere in between there is a band in which you can have both stable heavy elements and a functioning chemistry, and we are in it. Which brings us to the explanation that currently has the most support among working theorists, and I want to describe it accurately before I say what I think of it. If the fundamental constants are not fixed by any deeper law, but instead take different values in different regions of a vastly larger structure, then there is no reason to expect any particular value anywhere. There would be regions with every value, and the overwhelming majority would be sterile. No carbon, no chemistry, no observers. And the values you find yourself measuring are, necessarily, values compatible with the existence of something capable of measuring. That is the anthropic argument, and it is not stupid. It has one genuine success on its record. In 1987, Steven Weinberg used exactly this reasoning to argue that the cosmological constant, if it was not zero, had to be small, because a larger value would have torn the universe apart before galaxies could form. He put an upper bound on it from the requirement that observers exist. 11 years later, 2 teams of astronomers measured the acceleration of the universe and found a cosmological constant in the range Weinberg had indicated. That happened. It is the strongest argument the anthropic camp has, and it deserves to be taken seriously. But apply it to alpha and look at what you actually get. It tells you the number sits inside a habitable band. It does not tell you the number. It does not distinguish 137.036 from 134 or 141, because those would all work fine. It has no mechanism, no equation, no prediction that could fail. It converts the question from why is the number this value into why are we somewhere the number permits us, and those are not the same question. And the second one is very much easier. I am not going to pretend to be neutral about this. Every previous time physics has been confronted with an unexplained number, the eventual answer was a deeper theory. Why is the periodic table shaped the way it is turned out to be quantum mechanics and the exclusion principle? Why do the spectral lines split turned out to be relativity and spin? The anthropic argument is the first answer in the history of the subject that is structurally incapable of being that, because it does not point at anything underneath. It says the number has no explanation, and that our inability to find one is the correct outcome rather than a failure. That may be true. It might genuinely be the situation we are in, but it is worth being clear that adopting it means accepting that the question Pauli put in his Nobel lecture, the question Feynman said good theorists keep on their wall, is not a hard question awaiting a hard answer. It is a question with nothing behind it. And that is roughly where the field stood in the autumn of 2018, when one of the greatest mathematicians of the 20th century walked onto a stage in Heidelberg and said he had solved it. Michael Atiyah was, by any reasonable accounting, one of the 2 or 3 greatest British mathematicians of the 20th century. He won the Fields Medal in 1966 and the Abel Prize in 2004, which are the 2 highest honours the subject has. With Isidore Singer, he proved the index theorem, a result that connects the solutions of differential equations to the shape of the space they live on, and which turned out to be so central to theoretical physics that it underlies large parts of modern gauge theory and string theory. He was president of the Royal Society. He was Master of Trinity College, Cambridge. He held the Order of Merit, which is limited to 24 living people at any time, and is in the personal gift of the monarch. On the 24th of September, 2018, at the Heidelberg Laureate Forum, he gave a lecture in which he announced that he had proved the Riemann hypothesis. The Riemann hypothesis is the most famous unsolved problem in mathematics. It has stood since 1859. There is a $1 million prize attached to it, and essentially every serious number theorist alive has thought about it. He said he had done it in 5 pages, and he said the proof came out of a construction he called the Todd function, named after John Arthur Todd, who had been his teacher at Cambridge, and in the material he circulated around the same time, he made a second claim, which is the one that concerns us. He said the same construction gave the fine structure constant, not a bound on it, not an approximation. He claimed a mathematical procedure that generated the inverse of alpha to arbitrary precision, and that the value it produced matched the measured number to the accuracy of the measurement. The reaction was immediate, and it was not kind. Within days, physicists and mathematicians who had read the manuscript were saying publicly that they could not follow the argument, that the definition of the Todd function was not adequately specified, and that the derivation did not work. Sean Carroll wrote a piece making the objection that I think is the fatal one, and it is an objection you are now equipped to make yourself. Alpha is not a number. It is a function. Its value depends on the energy at which you probe. 137.036 is the reading at zero momentum transfer. 129 is the reading at the mass of the Z boson. Any purely mathematical construction that outputs a single specific value is answering a question that does not have the form the physics requires. It is like producing a proof that the temperature is 18 degrees. Worse, the value the Todd function was claimed to produce was tuned to the low energy figure, which is the least fundamental of all the possible choices, because it is the one most contaminated by the accumulated screening of every charged particle in existence. If a deep mathematical truth were going to generate a coupling constant, that is not the one it would generate. The paper was submitted to the Proceedings of the Royal Society A. It was never accepted for publication. Colleagues who had seen the work in advance had reportedly tried to talk him out of presenting it. He gave the lecture anyway. Michael Atiyah died on the 11th of January, 2019, 3.5 months after Heidelberg. He was 89 years old, and his wife Lily, to whom he had been married for over 60 years, had died earlier the same year. I do not think there is a way to tell that story that makes it comfortable, and I am not going to try. But I want to put it next to the other two, because at this point the pattern is impossible to ignore. Arthur Eddington, the man who confirmed general relativity, spent the last 15 years of his life trying to derive this number from pure reason, and died with the manuscript unfinished and his reputation in ruins. Wolfgang Pauli, the conscience of physics, the most feared critic in the profession, spent 30 years corresponding with a psychoanalyst about whether this number might sit at the boundary between mind and matter, and died in a room that carried it. Michael Atiyah, Field's Medal and Abel Prize, stood up at 89 years old in front of an international audience and staked what was left of his reputation on a 5-page derivation that his own colleagues had begged him not to present. 3 of the most decorated minds their fields have produced. 3 attempts, separated by roughly 30 years each. 3 failures, and in 2 of the 3 cases, public humiliation attached to a life's work that deserved better. And there is a 4th category I have barely touched, which is everybody else. Stephen Wolfram has looked for it in his computational models. String theorists have looked for it in the geometry of compactified dimensions and found not one answer, but an estimated landscape of possible vacua so large that the usual quoted figure is 10 to the power of 500. Numerologists have found expressions involving pi and the golden ratio, and combinations of small integers that reproduce the digits to whatever precision was current when they were writing, and every single one of those expressions has been killed by the next decimal place. That last point is worth dwelling on, because it is the quiet executioner in this whole story. Every numerological formula for alpha that has ever been proposed has been destroyed by improved measurement. Not argued against, not refuted philosophically, simply run over by a better experiment. Eddington's integer died when spectroscopy improved. The formulas that matched 137.036 died when the 4th decimal came in. The ones that matched to 7 digits died at the 9th. The number keeps producing more digits, and the digits keep being arbitrary, and every attempt to find a pattern in them has been correct exactly up to the precision available at the time of writing and wrong immediately afterwards. That is not the behaviour of a number that is hiding a formula. That is the behaviour of a number that does not have one. Which brings me to the thing I have been circling for 2 hours, and I want to state it as plainly as I know how, because I think it is both true and almost never said. Physics has never explained the value of anything. Take that seriously for a moment. Go through the whole subject. Newton's law tells you how gravity depends on mass and distance. It does not tell you the strength of gravity. That is a number you go and measure. Maxwell's equations tell you how electric and magnetic fields relate to charges and currents. They do not tell you how much charge an electron carries. Quantum mechanics tells you how states evolve. It does not tell you the mass of anything. The Standard Model, which is the most complete description of matter ever assembled, has somewhere between 19 and 26 free parameters, depending on how you count the neutrino sector, and every single one of them is a number that a human being had to go into a laboratory and measure and then type in by hand. Not one of them is derived. Not one of them has ever been derived. In 400 years, no equation in the history of physics has produced a dimensionless number out of nothing. Every law we have is a law about relationships. If this, then that. If the mass is doubled, the force doubles. The entire architecture of physical science is a machine for converting numbers into other numbers, and it has never once manufactured a number from first principles. So when Feynman says we do not know what dance to do on the computer to make this number come out, he is not describing a gap in quantum electrodynamics. He is describing the shape of physics itself. The tool has no facility for this. It never has. We simply did not notice, because for most of history, there was always a deeper layer to go to. And going deeper always turned one arbitrary number into a relationship between other numbers, and we called that an explanation and moved on. Alpha is where that runs out. It is where you go down one more layer and find that there is no layer. And I want to be honest that I do not know how to think about this. I have gone back and forth on it for a long time. There is a version where a future theory does produce the number, and everything I have just said looks like a failure of imagination, and I would be pleased to be wrong. There is another version, and it is the one that keeps me up, where the demand for an explanation of a value is a category error that we have been making since the 17th century without noticing, because until now the universe has always been kind enough to provide another layer. If that second version is right, then the bottom of physics is not a law. It is a list. A short list of numbers with nothing underneath them. Not derived, not caused, not implied, not required, just present, the way a phone number is present. And you are made out of one of them. I mean that literally, and I want to close by tracing it, because it is the part that does not stay abstract. The size of every atom in your body is set by alpha. The distance an electron sits from a nucleus is fixed by the balance between electromagnetic attraction and quantum mechanical spreading, and that balance is alpha. The strength of every chemical bond holding your proteins in shape is alpha. The energy of the photons your retina absorbs, the reason those photons are in the range your chemistry can process at all, is alpha. The carbon in you was manufactured in the core of a star that died before the sun existed. Through a resonance that sits at 7.65 million electron volts, because the electromagnetic repulsion of 6 protons very nearly, but not quite, cancels the nuclear force binding them. Move alpha a few percent, and that resonance moves off its mark, and the triple alpha process stalls, and the universe fills with helium and stops. There is no carbon in that universe, no chemistry complex enough for anything, no stars with planets made of rock and iron, because there is no iron. You exist because a number that nothing in physics can account for happens to sit where it sits, not approximately where it sits. There is a window, and it is not enormous, and we are inside it, and nobody can tell you why. Pauli understood this before almost anyone, which is why he told the Swedish Academy that quantum mechanics was unfinished business. He spent the last 26 years of his life trying to find the place where the number came from, and he looked in physics, and it was not there. And he looked at the boundary between physics and mind, which is the strangest thing a man of his rigour ever did, and it was not there either. On the 15th of December, 1958, he asked his assistant to look at the door, and the coincidence meant nothing. I have said that already, and I will say it again, because it is true, and because the alternative is a kind of thinking that ruins people. A hospital administrator assigned a bed. That is all that happened, but the man in the bed had spent his career being the most exacting critic in physics, the one who would not let anybody get away with an unjustified step, and the thing he could not let go of at the end was that the theory he helped build had a number in it that came from nowhere and that nobody could account for, and that the entire structure of matter, including the structure of the man lying in the bed, was resting on it. That has not changed, not in one detail. The number is still there, it is still measured, never derived. 2 of the finest laboratories in the world still disagree about its 10th digit, and neither can find the error. The committee that publishes it still has to widen the uncertainty by a factor of 2.5 to make the data stop contradicting itself. And every physicist working today, on every problem in every field, is standing on a value that arrived without a reason and has never once been asked to justify itself. Feynman said good theorists put it up on the wall and worry about it. They are still worrying. It is still on the wall. And in 110 years, since Sommerfeld first wrote it down in a wartime paper about the shape of hydrogen lines, not one person has been able to say where it came from. The number does not appear to be hiding anything. That is the possibility nobody wants to say out loud. Not that the answer is difficult, that there is no answer, that reality is not the kind of thing that has reasons all the way down, and that at some depth the explanations stop and a bare quantity is simply there, holding up every atom in your body with nothing beneath it at all. 137.03599177. And whatever comes after that